So let's continue with our lesson. You can just bear with me to have everything back on screen. Right. So we're continuing with lecture 3, and now we want to look a bit more at data accuracy. Okay. So how do we define accuracy? Accuracy is defined as closeness to the truth. So when applied to spatial or geographic information or variables, it refers to measurements of how often or by how much your data values are in error. All right. For example, we say 4% of a field was recorded as row crops, but in truth and in fact, they are perennial grasses. So we have an error of commission here. So we can actually identify a 4% error there. So remember we talked about describing spatial accuracy in terms of your map location as well as your attribute information. So this particular example refers to your attribute error. Okay. Now, spatial data accuracy describes how well digital representation reflects the true shape of a feature, the location of a feature, and also the characteristics, other physical characteristics. All of these will be represented on your map. So all of these, in terms of shape, location, and other characteristics, size, etc., we can actually categorize this as saying that we are describing the geometry of our map. All right, so these are some words, keywords I need for you all to remember and understand. So when we talk about geometry, we're talking about the location of the features, the shape of the features, and the size of the features. So we can actually describe the geometry of our map and give a representation of the level of accuracy there, as we mentioned in one of the previous slides. For example, plus or minus 5 meters. Now, inaccuracies may be introduced into your data during the following: the collection of the data. So when persons are out there on the field collecting the data, or the data is collected using other types of instruments such as satellite imagery, etc. Inaccuracies or errors can be introduced during the reduction and organization of the data. For example, what we're talking about here is after you collect your data, you'll have to clean up and organize the data because there may be inherent errors in there. You may have to convert the data into other formats. So everything that you have to do to the data, there's always a risk that you could introduce errors. Or when you let's say classify your data or manipulate your data, analysis of your data can also introduce errors into your data. So let's talk about data accuracy now from the perspective of our raster data. Now remember, we have our vector data and we have our raster data. We've talked a lot about issues concerning accuracy with vector data in terms of the map data and the attribute data. Let's have a look at what kinds of issues we deal with from the raster data. So the raster data sets, because of the fixed cell configuration, cell size configuration, so remember the cells will have a size or a dimension, all right, and we refer to that as cell resolution. So what is the concern about the cell size? This limits your positional accuracy to no more than half the cell resolution on average. So in other words, if you have a 10 meter cell size or cell resolution, what we're saying is the accuracy of the features that fall within that 10 square meters, the accuracy level would be no more than 5 meter accuracy. In other words, you could possibly have a 5 meter error there, right? Because remember, if you have a 10 square meter size cell resolution, you really cannot determine precisely where within that 10-meter square a point feature actually falls. All you can say is that it falls within there. Or typically also, if you have other features that are, the size of the feature is also smaller than the than half that 10-meter size, which is 5 square meters. If it's smaller than that, it means you cannot really determine much about the location or the size of that feature because it's smaller than that half cell resolution. So you have a bit of uncertainty in terms of positional accuracy with the use of the raster data model. So the raster data cells, remember how it works, it assumes a homogeneous pixel. In other words, it will assign a numeric value to the entire cell, even if you have other features occurring within there, and particularly if those features are smaller than half the cell size. So thus, if more than one phenomena or value is found, it is not reflected because you can only assign one value. All right. Um, that is, inclusion exists that is not accounted for. All right. Remember what those cells look like. For example, you have the raster representation, which is nice, smooth, and clean. For example, imagine this is a river. The raster representation of that will look like this. So it's the same feature, but it looks like this. All right. And notice how where you have nice clean lines, you have jagged lines here. So you can't really tell, for example, how wide this river is because an entire cell has been, entire cells have been assigned the value of the river. Other sources of error, okay. So how the features are conceptualized. Example, using raster representation to show generalized soil types when vector would have been better. For example, maybe you wanted to generalize your information as I mentioned before. So if you want to generalize information, vector is quite suitable. But if you want details of your soils, raster would be more appropriate because remember from a previous lesson, we said we use raster to represent continuous data. And in the real world, if you want details, remember soils change from one soil type to another by transition. There is no abrupt change. All right. So if you want detailed representation of that, the raster would be better. If you want generalization, vector would be suitable. So it all depends on what you want. All right. And depending on your purpose, you make a choice as to which one is appropriate. So if you choose the wrong one, you will have inaccurate information. Also, choosing inappropriate methods for data collection and analysis. Example, using aerial photos for mapping when ground surveying would provide more accuracy. Human error can also introduce errors into your data. For example, you may have data technicians that they are misunderstanding and misinterpreting information regarding how to use equipment, or the how to conduct your data collection method. So misunderstanding and misinterpretation there. You may also have errors in terms of keyboarding information into your database or even digitizing maps, lines, and features on your maps. Um, Errors can also be introduced into your data when outdated information is included. So your data is not current, it's not up to date. And if it's not up to date, you will not get a realistic output from your map analysis. Spatial uncertainty in your GPS positions, your global positioning systems, um, equipment may produce poor results if the equipment is not properly calibrated. This is a very common problem. You must have proper calibration of the equipment. Um, Additionally, if you're capturing data from whether it's satellite images, or for aerial photos that uses camera lenses. There may be distortion in camera lenses. Scanners may produce errors as well if they are not if they are not properly aligned as well. And additionally, you can introduce errors, as said before, in terms of processing of your data and manipulation of your data. So those may include both human and equipment error. And the important thing to remember is the quality of the data that you put into your GIS will determine the quality of the data that you get out of it. So it's very important to be very mindful of all of these issues. So ways of describing spatial accuracy. Okay, so documenting spatial data accuracy is necessary because it helps us to determine what the data set can be used for. So again, positional accuracy, this defines how close the location of objects represented in a digital data set responds to true location. It is more accurate if the distance between true location and the recorded value is small. For example, there, what I said before, locational accuracy represented as plus or minus 5 meters is actually more accurate than plus or minus 10 meters. As well as the reported as an average of a group of observations, that is positional accuracy. So you don't want to record just one observation to determine accuracy, but you want to have a group of observations so that you can increase precision. So speaking of precision, what do we mean by precision? How far a set of repeated measurements are from the average measurement, right? So if your measurements, you have a set of measurements and you have large variations in those values, it means then that you have low precision, all right? And precision is often a reflection of accuracy. So a set of measurements may be precise but not accurate. So even though precision is a reflection of accuracy, you can have poor accuracy and high precision, right? So for example, repeated measurements that are clustered, so you have a lot of them clustered in the same area. We're thinking in terms of a map now, but yet they are not near to the true value, all right? But at the same time, you want to remember that poor precision often leads to poor accuracy. So here we can get a visual of what we're talking about. So we're using these illustrations here. You have a little, like a dart board and dots, and the red dot represents our true location, right? So, and these little yellow dots represent our dots. So if our dots are clustered in this area, it is an indication that we have high precision, right? Because the values are located close to each other in terms of location. However, we have missed the point. We missed our goal right here. So they are far away from the truth or the true location, which is here. Hence the reason we describe this as having low accuracy and high precision. Let's jump to the far right because I don't really like this middle diagram too much. Whereas at the same time, if we were to get all our dots here on the red dot, then we actually have a situation where we can describe high accuracy and high precision. However, if we had low precision, see our dots are scattered. Notice it is distributed. I mean, it was aiming for the true location, but it didn't quite get it, all right, because precision is low. Had precision been high, we would have gotten this here. All right, so hopefully you all understand the concept of precision and accuracy. So how do we test for positional accuracy in terms of mapping? What we need to do if we have questions about locational accuracy, we need to use an independent source of higher accuracy. For example, first we want to find a larger scale map. Remember, the larger scale map shows us more detail. If we have a larger scale map, we can refer to that larger scale map in order to fill in gaps of information, right? So whatever locational accuracy or, for example, locational features we want certain about, we can go to that large scale map in order to get that information. Additionally, you can use GPS. For example, you can get your GPS equipment and go out into the field and do your field investigations to find the precise location of the features. This is what we call in surveying, engineering surveying, when they go out into the field to map, they call this ground truthing. All right, you actually go out into the field to investigate the truth of the feature. So you want to find the true location. And thirdly, you can use raw survey data. So that survey data is field data that the surveying engineers will collect out into the field with their equipment. So these measurements are taken in the field and are assumed to be of the highest levels of accuracy. So you always look for an independent source of higher accuracy to compare your GIS data to, that data that you have questions about positional accuracy. Now, with regards to attribute accuracy, this describes the closeness of your attribute values to their true value or true characteristics. For example, we talked about things like land use changing from one type to another, from, for example, agricultural use to residential use. Maybe your data had changed over time and it's not reflected in your database. You will need to, so this is attribute inaccuracy here, and you need to improve that. So again, that data improvement may also require ground truth, and you may have to go out onto the field to get that data. All right. So attribute accuracy must be analyzed in different ways depending on the nature of the data. Other examples of attribute accuracy on maps, let's see. For example, for categorical attributes such as classification, so we classify it into groups now of polygon or area features. The problem includes, let's see, for example, you're classifying a polygon as polygon A, so that A means something, when it really should be B. So that's incorrect classification. So for example, land use was assigned, a land use polygon or area feature was assigned as a shopping center. So that would be A, when instead it's actually a golf course. It should have been B. Other examples, most polygons are heterogeneous in reality, meaning it's not one value, but you can, the way the features are designed and represented with polygons, just as with a cell, you can only assign one value, when in truth and in fact, other features may fall within that polygon. For example, vegetation zones where the area may be 70% A and 30% B, you can only assign one value. So you may make a judgment call and decide, okay, well, the majority rules, I will assign the polygon as A. All right. Also remember, polygons A and B, those are two separate polygons. They may not be well defined, and you may not be able to identify the class clearly as A or B. So, for example, we were talking about with soils and soil classification, that transition from one soil type to another. It's very difficult to classify, particularly if you're using a vector format. So it would be more suitable to use raster classifications if you want to include that level of detail from one soil type to another. Other sources of error. So again, the age of the data may be too old to be useful or relevant with your other GIS data sets. When your data is old, it brings into question the reliability of the data. All right. The area of coverage, meaning incomplete geographic coverage. For example, you may have, let's say, a satellite image, for example, where some parts are covered by cloud cover and then other parts are clear. So it's incomplete data. Other examples, your soil map may be incomplete at borders and transition zones. So you have gaps in your data. When you have gaps in your data, again, that can also create a problem in terms of data accuracy because you have gaps in information. So then your output would be unreliable because of that gap in information. Map scales, we know map scales have the ability to show detail on a map. This can also affect the level of data quality. Again, remember, um, small scale maps generalize your data and give less detail. Larger scale maps gives you a whole lot more detail. So your map scale can introduce errors into your data if you're using the wrong type of map scale. So if you do have gaps in your data in terms of level of detail, how do you fix it? You need to look for surrogate or secondary data to fill in the gaps in information. Secondary data may include aerial photos. For example, you can look at your aerial photos to fill in gaps in information about habitats or forest types, etc. Other sources of errors could be your format, your file format. So methods used for formatting digital information for the transformation or conversion of your data, methods used for storing, and methods used for processing, as we would have mentioned in a previous slide, these may introduce error into the data. For example, converting your map from one scale to another. For example, trying to convert it from from small scale to large scale is a problem. You can what you want to bear in mind, you can convert from large scale, meaning detail, to small scale, meaning generalization with less error. But small scale to large scale will give you a lot of error. You can introduce errors by when you try to change projections as well from one map projection to another. If you try to convert from raster to vector or, or vice versa. All right, so you can actually change those types of data models as well. And every time you do a conversion of any type, you also add the possibility of error because the inherent errors are now exaggerated. Error may also be introduced based on the density of observations, the number of observations you made in the area. So a rule of thumb you want to remember, the larger your number of observations or readings that you take in an area is the higher your level of accuracy. So where you have an insufficient number of observations, it may not provide the level of resolution, or in other words, detail. So resolution is a word you want to remember. It's always associated with detail. Insufficient number of observations gives you a low level of detail. So the closer the sampling intervals are, if you think back to the previous map with the dartboards, the closer the sampling intervals are, the more accurate it is. So you're talking about clustering. You have less, so between the sample points, the closer they are to each other is the less assumption that you have to make. Relevance. Let's see, what do we mean by relevance in relation to data error? So where desired data regarding a site may not exist, because that happens too, surrogate or secondary data may be used instead. But if you're using alternate data or surrogate data, you must have a valid relationship between the surrogate data and the particular phenomenon that you're studying. Otherwise, so that valid relationship is what we're talking about in terms of relevance. It must be relevant for, so if you don't have a proper relevance between them, error will creep in because there's no direct measurement for the phenomena. For example, you where you have you're using soil type in an area, in a study area, to determine forest type. So there is relevance in that example because forest type, we know that one of the things that should determine the type of forest is the type of soil that you have. Okay, so you can make an inference here. Also, accessibility to data. For example, what is open and readily available in one country may be restricted, classified, or unobtainable in another. So if you have a GIS project that requires a particular data set in order to carry out your analysis, you may not have access to a particular data set or to certain parts of that data set if it is of national security concerns. So it means then that you're going to have gaps in your data. Cost of the data can also provide a challenge in terms of introducing errors into your data. Costs can actually make accessibility difficult. For example, if you have extensive and reliable data that is often quite expensive to obtain, satellite imagery, for example, is very expensive. So if you are an individual or a private citizen trying to conduct some research, if you don't have those kinds of personal funds to put out, you probably not going to have access to that data. All right. So if it is costly, it now puts it out of your reach. So it's actually not accessible to you. So I would like to thank you for joining me for today's lesson. Please refer to eClassroom for details on this week's activity. Thank you.